Hello. In this video, we'll introduce geometric and arithmetic sequences. This is the second video for section 2, so let's get started. So first, we have recursive formulas. These are a little bit funky when you first get introduced to them, but they make more sense over time. A recursive formula uses the previous terms to define the next term. So in this here, we have our sequence term, and then we also have our previous term. When we say ace of n minus 1, what we're asking for is the n minus 1 term. So if this is the n term, this is the term right before it, and then we're just going to add 2 to it. This is an arithmetic formula, and we'll go over that and exactly what that means in a minute here. So also when we do recursive formulas, we have to define what terms we start with, because how do we get the first term if we don't know what the 0th term is if we're starting at 0? Of course, we don't start at 0, we start at 1. But we start with this first term. So in this, we had to say the first term is 1, so if we want the second term, we would do 1 plus 2. If we want the third term, we would do 3 plus 2, and so on. Famous example of a recursive sequence is the Fibonacci sequence. In this case, this term is equal to the sum of the last 2 terms. It works exactly the same as this one. For practice, it would be good to put out a couple terms of this. Ace n of 1 equals 1, and ace n of 2 equals 0, if I remember correctly. And it derives the golden ratio. So, recursive arithmetic sequences. The terms of an arithmetic sequence have a common difference. That means between each term, we're adding or subtracting a constant amount. So our basic sequence rule for recursive is exactly like it was on the previous page. We have our new term, the previous term, and plus some constant d, where d is that common difference we just talked about. So for an exercise in this section, try to do the first 6 terms of this sequence. Okay, and I will show you how to do this on the paper.
Hello, welcome to the paper for the first time. For this example, we'll be doing it on the paper. Welcome to the paper. This is the first time on the paper in this video. Examples are on the paper. Information is in the presentation. So for our example, we want to find the first 6 terms of the sequence ace of n equals ace of n minus 1 plus 4 if ace of 1 equals 2. So we then will add 4 to this, because for ace of 2, because we're just adding 4 to ace of 1. So it equals 6, and so on. We repeat this process because every time this ace of n minus 1 is just the previous term, because that's how a recursive sequence works. So 10, ace of 4, let's just write the rest of these out for convenience. So then we have 14, 18, and 22. So this is our common difference, and this is the previous term. Back to the presentation.
So moving on, we also have recursive geometric formulas. A geometric sequence have a common ratio. This means we're either multiplying or dividing a constant amount between each section. So we can see we define recursive geometric sequence with the following formula, which is we have this new term, this is the last term, times some constant r. If this was a fractional constant, we would do division, and if it was negative, it would kind of jump between negative and positive. I'll show you more of that when we go to the example. We see that r is this common ratio. For an exercise, what are the first 3 terms of this following sequence?
Welcome to the paper again. This time we'll be doing a geometric recursive. So first, let's define our sequence. We're defining the sequence as ace of n equals ace of n minus 1 multiplied by 2. We want the first 3 terms. We also define ace of 1 equals 2. This here is the common ratio r, and this is our last term. So when we have a of 2, we just take our a of 1, multiply by 2. And a of 3, we'll take this term and multiply it by 2 again. And we get our first 3 terms.
Moving on, explicit formulas output the term at a given index. The previous issue we had with recursive formulas is we would need the previous term, which means, say, if we want the 100th term, we need the 99th term, which means we need the 98th term, and all the way back down to 0. And that gets really tedious really quickly. So explicit formulas allow us to just spit out the value given the index. We saw explicit formulas in the introduction to sequences video. All of those were explicit, how we just kind of plugged it in. So this is our basic form for the explicit arithmetic formula. This is a current term. This is our starting value, so for the very first term, plus n minus 1. The n minus 1 is here, otherwise we would have to start counting from 0. Or we can start counting from 0, and then we'll just have 0 times d to get our first term. Or when we do the n minus 1, when we put in 1, we'll get 0. And we multiply that by d. Multiplication makes sense here, because multiplication is repeated addition. And what we're doing is repeating addition between each step. We also have a basic explicit form for the geometric formula. We see the same n minus 1 because we need this to be something to the 0 for our first term, and because something to the 0 equals 1. And that is simply multiplied by our starting value. And again, exponentiation makes sense here because exponents are just repeated multiplications. So for an exercise, find the 20th terms of both of these sequences. If the common difference is 10 for the arithmetic sequence, the common ratio is 3/2 for the geometric sequence, and the starting value for both sequences is 1.
For this final section of the video, we'll be doing it all on paper. So first, for the example, you must find the 20th term of 2 sequences. Our first sequence is a of n equals 1 plus n minus 1 times the common difference 10. So we want to find the 20th term, and we can just plug this into our calculators. So we can do, in our function menu, like you would normal functions, x plus 1, we would just replace n with x minus 1, times 10. And then we can use the table if we want a bunch of terms, or we can also do alpha, trace, enter our function, and then just do 20, and we'll spit out 191. That makes sense to me. So the way that this works here, so we have this as our common difference, and this is our initial. Because this value at our first term will be equal to 0, because 1 minus 1 is 0, and we multiply this, so this cancels out. We just have our initial term left over. The other sequence we need to find is xn, which equals 1 times 3/2 to the power of n minus 1. And we want the 20th term. So once again, this is going to be our initial term, and this here is our common ratio. And once again, we can plug into the calculator. 1 times, we can use this for fraction, 1 times 3/2 to the power of x minus 1, and just do y20 again, and we'll see that it equals 2216.8 3, 8. So sequences don't always have to have positive or whole number outputs. They could also have negative outputs. Like we could have a negative common ratio, say if we wanted to do an equals 1 times negative 1 to the n minus 1. This sequence looks something like 1, negative 1, 1, negative 1, and so on. Just because the negative 1 being multiplied over and over again changes each time. Once again, the initial term works because at n equals 1, this equals 0. And so this term, because something raised to the power of a number 0 is 1. So we just get 1 times 1, and this ends up being the initial term. So for the final part of this video, we'll go over finding the common ratio or difference of a sequence given two terms of the sequence. So we're going to start with finding a common difference. Say we're given ace of 2 is equal to 4, and ace of 8 is equal to 40. How do we find the common difference between them? So what we can do is subtract the difference of each one. So 40 minus 4 equals 6 times the common difference. Because we're applying the common difference 6 times between 8 and 2, and we're applying the difference between our actual values is 40 minus 4, or 36, equals 6 times d, which then, because 6 divided by 36 divided by 6 equals 6, we can know 6 equals d, and we can try that in the calculator by doing 4 plus 6 times 6 equals 40. And that is our answer. We can also do this similar process with geometric sequences. So let's say we have x of the second term equals 2, and the sixth term equals 100. So we can do 100 minus 2 again, getting our difference, equals the common ratio to the power of 4. This works the same way as the other one, how we used multiplication to show the repeated change in arithmetic sequences. Instead, in this case, we're showing the repeated change in a geometric sequence. 98 equals r to the 4th, and then that's just will be the 4th root of 98. If your calculator doesn't have a 4th root button, or it's inconvenient to access, you can do 4 to the power of 1/4, or a number to the power of 1/4. So in this case, we'll do 98 to the power of 1/4, and that will be that number. We're not going to worry too much about it. For now, we'll just write 4th root of 98. Really, I should have designed the problem in a way with a constant common ratio, but it's fine. It shows the point. There's also more rigorous ways to do both of these, and they might be important for more theory-based things, but for ACDEC, they're kind of a waste of time. This way is faster. That should be all for this video. In the next video, we will cover a series where we add up the terms of the sequence. Thank you.